Today I will be presenting my work that I've been doing with Teeth. It's about using ANNs for accelerating parameter inference. Before we go to ANNs, I would like to discuss about parameter inference so that we are all on the same ground. So to describe it in a few words, whenever you have an observed data X and you have a model that predicts this observable, that is parameterized by some parameters theta, and you want to know what are the model parameters that are allowed by your observed data. And typically you will have some errors in your observed data which will lead to a range in your allowed values for theta. Now typically we use a Bayesian framework to do this thing, where the whole game now becomes one of calculating the posterior given the likelihood and the prior, and most of the times the evidence is not known because it can be computationally expensive, especially for simulations. So in those cases, instead of computing this analytically, we go to MCMC, where it becomes a iterative thing where you sample from the prior, you run a simulation, you calculate the likelihood by comparing with the observed data, and you have some acceptance criteria based on which you accept this sample or not, and then you create a chain of samples that, as it converges, becomes statistically equal to your posterior. But now there are a few problems with this conventional MCMC based approach. Two of them are: first, it is very inefficient, especially when your number of parameters in your model becomes very high. The number of simulation runs you need to do for the MCMC to converge goes exponentially. Secondly, when your individual likelihood computations are very expensive, then also this becomes very this MCMC becomes very expensive to run, and when these two issues are combined, MCMC becomes unfeasible to do. So a possible way out to solve these issues has come up in recent years is to use emulators. What emulators are basically you run your model at a predetermined set of points and you train an emulator which will then interpolate the model output at other parameter points in a very fast and accurate way. But for reionization studies, because you have high dimensions, you can't use normal emulators, you need to go to machine learning based emulators, and these have been shown to give very fast and accurate interpolation results, and these are been widely used in reionization studies on all these papers. Specifically in 2023, 2024, there were two papers from our group which showed that you can use GPR based likelihood emulators. Typically we have not used likelihood emulators before. In all these papers they typically directly emulate the observables, but we have shown that if you use likelihood emulators you can improve parameter inference and you can reduce the number of simulation runs required by up to 30 times. But we also know that ANN based emulators or artificial neural network based emulators can be much faster in both training and prediction compared to GPR and other ML based methods. So our goal in this work was to extend the work that was done previously using GPR to ANNs. So to do this we use a test bench where our model is script, the semi-integral code for reionization with photo conservation, which is a reionization code that gives us the reionization state and the thermal state of the IgM at a given redshift. We use a box size of 256 comoving inverse megaparsec, H inverse, and we run the simulations at two different resolutions of 32 grid cells and 32 cube grid cells and 64 cube grid cells, and our model is parameterized by 5 parameters, and we use these observational constraints which are the CMB optical depth, the lower limits on Eisen fraction, the galaxy UV lift data, the low density IgM temperature estimates, and also we put a constraint that reionization must end by redshift 5. So our approach in this work is to, so this was your typical MCMC flow chart. So what we did was we replaced this part by an emulator. So you do not need to run the simulation at each time, but you can just call the emulator, it gives you the likelihood directly and you can accept it or reject it as you please. So first we have in the literature most of the emulators were trained using Latin Haplogroup samples, so we followed suit and we chose 10 to the 4 random parameter sets using Latin hypergroup sampling from within our prior range, which is 10 times lesser than what was actually needed to do a full MCMC. For these 10 to the 4 random parameter sets, we ran simulations at the required resolutions and calculated the chi-square values. We split them into trained test sets as is standardly done for training emulators, and we trained ANNs with varying hyperparameters. So when I say hyperparameters, I mean the neural network's length, the number of neurons in each layer, the learning rates, etc. And after this is done, we select the ANN that has the best test R2 score and use this to now do an MCMC by putting it here. So using Latin hypergroup samples, the results are this. They are not very good. So the blue one is what we are actually trying to replicate, and the green is what we get. So then we tried to artificially reduce the prior and sample with the prior reduced, but even then it starts to go near what we actually want, but it never really reaches there. And the reason this does not work is pretty apparent if you actually look at what is happening. So this is a slice from our parameter space. This is a full prior, and these are the blue points are the Latin hypergroup samples that we took, and the red part is where we actually want them. These are my high likelihood regions, and this is my actual posterior that I am trying to replicate. So even if we take 10 to the 4 samples here, the number of samples in this region is very sparse. So emulator will never be able to learn very well what is happening in this region. So what we actually need is a number of samples much larger in this region, and we do not actually need these samples. So what we do here instead is we use script's convergence with respect to resolution, which means that in script, for a given set of parameters, even if you change the resolution, the output does not vary. So using that, we use a solution where we run a very coarse resolution MCMC, which is very inexpensive. We use a 4-cube MCMC, and using this MCMC chain, we take random samples from this, run high resolution simulations, and then use that to use our training data. So this is our new training strategy. So we run a very low resolution MCMC using inexpensive co-resolution simulations. We randomly select a small number of parameter sets, but now the problem is that we do not know how many training sets we actually need for the ANN to converge. So what we do is we run the simulation required high resolution 32 cube and 64 cube, compute the chi-square values, and then we, as was done before for the Latin hypergroup case, we standardize the data, we split it as required, we train the ANNs with very high parameters. But now once ANN is trained, we use it to predict the chi-square values for a given validation set that was not seen during training. And then once this is done, we train a neural network with more data and do a prediction again and see when these two predictions, we are computing the relative entropy between these two predictions, we see when this relative entropy drops below a certain threshold that we have defined. When that is done, we say that this ANN has been trained, and then we can use it to do our MCMC as we want to. So this is the result using for the 32 cube case. We see that the red one is the full MCMC, and the blue one is the ANN based MCMC, and they are so on top of each other that you cannot even differentiate them. And you can see the full MCMC takes around 400 hours, while the ANN based takes 100 hours. This is not that great, but we'll see. And the simulation runs have gone down, number of simulation runs have now gone down 2 orders of magnitude. The good thing about using ANNs is that the time that it took in the 100 hours, most of it was used to train the ANNs. So if you use a very high resolution, if you go higher resolution, this factor will be much better. So to check that, we use the same formalism. We do it for the 64 cube case, and see what we see is that the full MCMC took 8,000 hours. Yeah. But our emulator based MCMC just took 150 hours. And this remains constant because number of parameters in our model is the same. So the number of simulation runs remains constant. And again, we see that the results are very good. They match almost exactly. But now we have gone from 1 year in computation time to just under a week. To summarize, using MCMC based inference, we have shown that MCMC based parameter inference becomes unfeasible when your models are likelihood computations are high or your number of parameters are very large. We have shown that we can use faster, more efficient parameter inference techniques are needed for leveraging upcoming high resolution observations. And we have shown that ANN based likelihood emulators, when taking advantage of the model's convergence with respect to resolution, can dramatically accelerate the parameter inference speeds. Thank you.
So thank you for nice talk. I'm just slightly confused. Do you use this emulator on the fields or is it on the statistics?
So we use these on these observational constraints, not on the fields.
Okay.
On the chi-square, yes.
Likely. Okay. Yeah, but there are some papers which says that chi-square, emulation on chi-square might be wrong compared to the field and then computing the statistics. So, no, I mean, here it's okay, but there are some 11 alpha forest papers where it's not correct. So that's fine.
In this case,
Yeah, but
we had the full MCMC.
have you checked with the field?
Yeah, I'll check.
You have checked. Okay.
No, I have not checked. I will check.
Okay, fine.
Maybe I've asked you this before, but I don't remember. How many parameters do you have?
5 parameters.
Then it's a little surprising why you need so many simulations. So, for example, I'm coming at it from cosmological emulators. With 7 cosmological parameters, we needed 35 simulations. The Quixote Latin hypercube, again with 8 or 9 cosmological parameters, has 1,000 simulations. Do you know why you need so many more simulations in your case?
I'm not sure. Maybe it's because the priors in our case are very wide. Okay. But this is just what. So we use R-1 criteria in our. So R-1 is the Gelman-Rubin statistic that must go below 0.01. And that is what gives us this number of simulations as 10 to the power 5.
We can maybe discuss this. I'm a little surprised. No, that is okay. But how many simulations do I need to run to train my emulator? Yes. So that number I couldn't see on the slide.
That is
okay, then it's fine. Okay.
Yeah. So can I ask? Yeah. So have you tried using variational inference or normalizing flows? I mean, so my CS colleague Srijit has written a paper 3 or 4 years ago showed that variational inference is much faster than MCMC. Or is there any reason why variational inference doesn't work for solving this?
So this work was basically done to extend previous work using GPR to ANNs, but we have looked into normalizing flows and we wish to work in it in our next projects.
Okay, what about variational inference?
So that I have not checked it, I'll check.
So when you obtain your training sample based on coarse grain MCMC and then do the inference later based on that, is it similar to double counting of the information in any way?
Can you repeat?
So when you train your sample, like obtain the training sample using coarse grain MCMC, and then do the inference based on that training sample, the emulators obtained from that training sample. Is it like using the same information twice in any way?
No, it is not, because the initial MCMC that we do is a very low resolution one.
Yeah.
And for the training, we use the same initial MCMCs, only the parameter points, and then run a new high resolution simulation that contains the high resolution information.
Okay.
So that is our training data, not the initial MCMC itself.
Okay. Thanks.